других математических физиков 20 и 21 века, невероятно счастливые отношения с реальностью. Всю свою жизнь он опирается на чрезвычайно сложную абстрактную математику, но так сложилось, что 4 или 5 раз его предположения, которые на первый взгляд выглядят чрезвычайно странными, удивительными, экстравагантными, предположения о том, как устроен мир, получали экспериментальное подтверждение во всяких наблюдениях. Так было с его представлениями о черных дырах, так случилось с его одной совершенно теоретической работой, касающейся мозаики, которую можно выложить из двух элементов, которые имеют пятилучевую симметрию. Существенно позже ее наблюдали в структуру, которая называется квазикристаллы. И сегодня мы услышим еще об одной области его интересов, которая исходно абсолютно абстрактная, абсолютно теоретическая и приводит к совершенно фантастическому предположению об устройстве мира и о его истории, в которой он активно искал сотрудничество с астрономами, которые занимаются наблюдениями за космосом. И так случилось, что с некоторыми из них у него получилось очень продуктивное сотрудничество, и он и его коллеги видят в этом подтверждение в том, что так действительно устроен мир. Одна из его ключевых книг называется «Дорога к реальности». И выясняется, что в отличие от многих других математических физиков, реальность чрезвычайно важна для него, и реальность платит ему взаимностью. Сэр Роджер Пенроуз. Кажется, он претерпел суперпозицию.
It's a great pleasure for me to be back in Moscow. The last time I was here was in 1971, I think. And I also went to what was then Leningrad to see my grandmother's house. She lived in St. Petersburg in the late 1800s, and then went to Switzerland where she met my grandfather, and unfortunately she had never returned. But it was nice to see her house. Okay, so let me give you the title. I see you have it in Russian. The title is my title in English, which I hope is a translation of that into English. It's here. Seeing through the Big Bang into another world. Now, you might believe me or might not. I do mean what I say. This, another sort of milder title here, which is my official title for this subject, which is Conformal Cyclic Cosmology, which in English abbreviates CCC. That's nothing to do with the Soviet Union. Sure. And this is a basic introduction where I'm not going to give you any of the equations. So I hope that's all right. Now, before giving you this scheme, I used to lecture on this under the title of a sort of outrageous new cosmology or something like that. And after a while, I got used to the idea myself and I stopped calling it outrageous. So that's partly because I suppose familiarity means that I didn't think of it as so outrageous as I did originally. But first of all, before telling you my cosmological scheme, I want to tell you the conventional picture of the universe, and to draw the universe, as is what I usually do, I shall give you a space-time picture. So you see time is going up the picture like this, and you have to think of, well, the Big Bang is the initial point here, big explosion, and the universe expanded upwards. So as time goes up, think of sections through it like this as representing space at any one time. You may ask what all this funny stuff is at the back. And somebody, I forgot to explain in one lecture I gave, and somebody says, why has the universe got a hole in it? Well, the reason the universe has a hole in it in this picture is I did not want to bias the situation with regard to whether the universe is open or closed. It's easier to draw it if you imagine it is closed, so you think it's going all the way around here, but maybe it's not, and maybe it's open, and so I have these sort of wiggles going out there, and who knows. For the purposes of my talk, it does not matter whether it's open or closed. However, we do want the Big Bang, we do want this expansion here, it slows down a bit, and then we have this accelerated expansion. This accelerated expansion got the Nobel Prize. Well, I mean, physicists, it didn't get the Nobel Prize. The physicists who observed this expansion got the Nobel Prize, not the last year, but the year before that, the Nobel Prize for Physics. And this was not expected by them, and they tended to call it some mysterious dark energy. It's referred to as dark energy. However, to people who've been working in cosmology for many, many years, it's the sort of thing one would expect. If there is this term in Einstein's equations, there's a thing which we call lambda, I suppose you call the Russian for L, whatever that is, the thing which looks like the Russian L, and we call that lambda, and this is the term Einstein introduced into his equations in 1917 for the wrong reason. He wanted to have a universe that was static, does not expand, just stay there forever, and he needed that term in his equations to make it stay forever. But then shortly afterwards it became clear that the universe was not static, it was expanding. And so Einstein then changed his mind and withdrew this cosmological constant, this lambda thing. He withdrew it and said this was his greatest mistake. However, it turns out that even Einstein's big mistakes, this one in particular turned out to be true. So Einstein was right, that there is something like his cosmological constant, or lambda, or dark energy, or whatever you like to call it, which seems to be coming into play. We are, I should say, this is the history of the universe, we're somewhere up about here, where we're beginning to see this exponential expansion taking place. Now, there is one thing about this picture. It's supposed to represent our conventional present view of the universe. You might say, where is inflation? There is a thing called inflation, which is supposed to have taken place in the very, very, very early stages of the universe. Now, there are two reasons I have not indicated inflation in this picture. One of the reasons is, well, maybe I have. Because if inflation took place, it would be hidden right in that little spot at the beginning, and you wouldn't see it at all on the scale of this picture. So maybe inflation is in the picture, and we just don't see it. Well, there's another reason I haven't drawn it, and that is I don't really believe it. I'll come to that in a minute. But first of all, can we perhaps have a look at it? And in order to have a look at it, I'm going to need a very powerful magnifying glass. Here is my magnifying glass, and so I'm going to look at it and see what it looks like. Okay, so here is what it is supposed to look like. I should start from here. This is the handle of the magnifying glass, and there is inflation. So here, inflation, Big Bang is before inflation. So this is the conventional view. If you look at any modern cosmology book, whether it's a popular book or a serious scientific book, they will talk about inflation as though it really took place. Now, one thing I want to point out about this is it's very much like what we see for the exponential expansion of the universe in the remote future. So this is our remote future, and this is supposed to have been a phase which took place very, very near immediately after the Big Bang, a very, very tiny fraction of a second after the Big Bang. According to the inflationary model, this universe expanded like that. Well, I was never very happy about this idea when I first heard of it, partly because it was supposed to do various things which I didn't believe it did do. I thought, no, it doesn't do this. I won't say too much about that. I'll mention a little bit later the sort of reason I didn't believe that. But later on, there became good reasons for why inflation might have been there. And if you don't have inflation, you have to have something else which serves the purpose of inflation. And I'm pointing out this exponential expansion being very similar to what we see here. And the picture that I want to present you, obviously maybe it's not there, but in the picture I want to present to you, it is in a certain sense there, but it's not after the Big Bang, it's before the Big Bang. So that's a strange thought, and let me try and explain what I mean. In fact, that's more or less the purpose of this talk. As a lead up to that, I want to show you two mathematical tricks. Now these are just tricks which, as a mathematical physicist interested in cosmology, I've been applying one way or another for a long time, very many decades. One of them is to take the remote future and squash it down. So I squash it inwards until it becomes a finite boundary. Now, in order to explain a bit better what this is, let me show you a picture which may be familiar to some of you. This is a picture due to the Dutch artist M.C. Escher. It's called Circle Limit 1, and it's a picture of what's called hyperbolic geometry. Well, I noticed Lobachevsky here is the one, since I'm in Russia, this particular diagram is due to Beltrami, although people call it the Poincaré disk. It's one of these things in mathematics. Often the name attached to something is not really the name you should be attaching to it. Beltrami was an Italian geometer, and he devised this way of representing this geometry. Now, I'm not concerned with that geometry here. What I am concerned with is the kind of picture that we have here. It's what's called a conformal picture. You see these fish-like creatures, they inhabit this world. This is the entire world of these fish, right out to infinity. That's the entire world. Not just part of it, it's the entire world. That's the entire Lobachevsky geometry. Now, these fish in the middle look as though they're bigger than the ones that you get near the edge. But you have to imagine that if you were one of these fish, you would be just the same as one of these fish. And if you happen to be this one living here, you would think you were just the same as this one here. So the geometry gets squashed as you go out to the edge. But the particular character of the squashing is what's called conformal. Now, what that means is that angles, like the beak of this fish, I don't quite know why a fish has a beak, but never mind. The beak of the fish has the same angle wherever you see it. More seriously, notice the eyes of the fish. They are circles. And those are exact circles, no matter how small they seem to be near the edge. So the representation of the fish, according to this geometry, is a conformal representation. It means that angles are correctly represented, even though sizes are not. So when they look small to you or to me here, you have to imagine they're not really small. It's the representation which has squashed them down in this conformal way. Conformal means that as it gets squashed, these small shapes get preserved or angles get preserved. So when I do this squashing here about infinity, I squash infinity down. This is the same sort of trick as is used here. So Beltrami used that trick in this picture. I'm using it to squash down infinity. Now I'm using the trick in the opposite way to stretch out the Big Bang. So I'm doing two things. One is to squash infinity down, and that makes a boundary like the boundary you see here. You see the boundary is a circle around the edge, which represents infinity. In the same way, I'm representing the infinity here as this finite boundary. And these are what I call conformal. And I'll say a little bit more about that later on. Okay, so I'm squashing infinity down and I'm stretching the Big Bang. Now this stretching has the advantage that whereas it is what's called a singularity, a singularity is a place where all your equations go wrong. That's the idea. Things go infinite. Near the Big Bang you have infinite temperatures, you have infinite densities, you have infinite curvatures of your space-time. And so Einstein's equations just say, well, we give up. So that's the normal way that people think about the Big Bang. They think the Big Bang was a place where the physics simply invented itself or something like that. So it's not really where you're allowed to use the ordinary equations. They go wrong. Okay. So the trick here is to stretch it out so maybe you can use ordinary equations. That's the idea. So those are just two mathematical tricks. Now those two mathematical tricks, I want to say something more serious about them. But they're not just tricks, but in a certain sense, they're real. Not only are they real, but when I squash the infinity down and stretch